Okay, so if I break down the questions you guys been sending for 6-1 and 6-2, these two questions kind of encapsulate a lot of those issues. So let's look at them. I'm going to start with the one on the right, because that's the 6-1. I believe that's 6-1, number 5. And it's talking about finding the mean of a probability distribution. So in our probability distribution, we've got different possible outcomes and the proportion of times or the probability that those different outcomes will occur. So there's about a 10% chance that a 0 will pop up, about a 20% chance that a 1 will pop up, a little bit less than that a 2 will pop up, a little bit more than 26% chance a 3 will pop up, and about almost 24% chance that a 4 will pop up. So if you imagine we did this, say 100 times, if we did this 100 times, we'd have, about 10 zeros. We'd have about 20 ones. We'd have, about 19 twos and 27 threes and about 23, 24 fours. Now, that might not add up to 100 because of the rounding, but that's okay. So, and actually clearly doesn't. That's okay. Well, maybe it does. Doesn't matter. So if we wanted to find the average result for this probability distribution, often called the expected value for this distribution, we're not finding the average of these probabilities. We're finding the average one of these results that occur. And if you remember back to our frequency tables tended to look more like this, though they were usually drawn the other way. But where this was our frequency and this was our data or our value. So the zeros came up 10 times, the ones came up 20 times, again, approximately based on these percentages. And we had to take into account how often each of those values were occurring to determine what the mean was, what the average is. And one of the ways we did that was to multiply the value by how often it occurs. So we could take that 0 times 10 and the 1 times 20 and the 2 times 19 and so on, and then divide by how many we had, 100, to find an average value. Well, we can do a very similar thing with a probability table. But in a probability table, we're not given really how often each of these happened. We're given the probability of them happening. So we could do what I've kind of done here and imagine it happened 100 times and then use the percentages as amounts out of 100. That is what percent means, per 100. But really, all we need to do is take each of these values and weight them by their probabilities. So the 0 is happening what proportion of the time? It's happening 0.1061 as a proportion of the possible values. So it's happening, again, about 10% of the time. So that 0 is being weighted based on its probability. Plus, well, the value of 1 happens how often? 0.1991. So that value of 1 has been weighted by its probability. Let's, for sake of argument, imagine that these are dollar values. So let's say we're playing some sort of game, and in this game, there's a 10% chance we'll get no money, 19.9% chance we'll get $1, 18.82% chance we'll get a 2, 26.88% chance we'll get $3, and about 24% chance we'll get $4. So each of those amounts of money have to be weighted by their probability of occurring to figure out how much value we expect to get out of them. So each of these values are going to be multiplied by their proportion, their probability. Again, we can think of it as their weight. And then that sum is going to give us a mean. Now, you might be thinking, well, wait a minute, we're supposed to add together and divide by how many we have. Well, essentially, we're adding these up. We're based on how often they occur out of the 100%. Somebody remarked that, hey, these things all add up to 1, and they better add up to 1 if it's a probability distribution. So essentially, we're taking this and dividing by that 100%, if you want. But because in a probability distribution, that sum is always going to be 1, we don't actually have to do that. We can just multiply each of the values by their weight, by their probability, and that sum is going to be our mean, our X bar. You will often hear this kind of mean from a probability distribution called a weighted average for this reason. It's essentially an average weighted by the probability of occurrence. So it's just our mean. This is also referred to sometimes as expected value. Again, if this was a game, the average that we end up with here, whatever it is, looks like it'll be somewhere around, $3 and change if I had to make a guess. So that $3 and change is the expected value that we expect to get out of playing this game. So that result is going to be your weighted average, your expected value, your mean. Hopefully that helps. If not, let me know. Now, as we move on to 6.2, in 6.2, we're talking about binomial distributions. So in binomial distributions, we're talking about yes or no situations. So for example, here, the probability of being born with a genetic condition is 19 out of 20. So that means that's our yes or no. You either have this genetic condition or you do not have this genetic condition. And our variable is how many of these 170 volunteers do we expect to have this genetic condition? Well, if the probability of successfully having this genetic condition is 19 of 20, and we have 170 volunteers, if we want to find the most likely number of the 170 volunteers to have the genetic condition, this again is expected value. Most likely expected value. All of that is mean. So we're asked to find the mean here. Now, over here, I used X bar for mean, and frankly, I shouldn't have. I should have used mu. Why are we changing to mu for mean instead of that X bar? As you're reading through your sections, and you, again, make sure you're reading through your sections, the difference between the X bar being a mean for a sample, versus the mu, mean for a population, is the difference between using the Roman letters and the Greek letters. When we are representing something from a sample, we use the Roman letters, S and X bar and so forth. When we're doing a population, we use Greek letters, mu, and instead of S, sigma. Excuse me, for standard deviation. Now, why is this a population? Well, when we're talking about a probability, these are all possible probable outcomes. The fact that these add up to that 100% means this is the entire population of probabilities. So we're talking about a distribution of population values. Hence, we've got to use the population symbol, the mu, as opposed to x bar. So make sure you're reading through that section. But it's just a change in symbology. So when we know when we're talking about a parameter from a population versus a statistic from a sample. So find the most likely number, find the expected value, find the mean number of volunteers that have this genetic condition. Well, if 19 out of 20 are supposed to have this genetic condition, and we've got 170 people, well, that expected value should be the number of trials we have multiplied by the proportion of those that should be successful. Again, using successful as having this genetic condition. So if we imagine, what is that, 95%. So this is, if we want to write it as a decimal, 95% chance, or a 0.95 proportion. So if 95% of people are supposed to have this genetic condition, and we've got 170 people, then, well, 95% of those 170 people should have this condition. Now, again, you might say, wait, why is that different than what's going on over here? Well, it's really not. It's just we only have one probability that we're looking at. We don't have, all these different possibilities that we have to add up. We only have one possibility that we're adding up. So our mean is essentially a simpler argument. So we've got 95% chance that those 170 folks have a yes. So whatever 95% of 170 is, and you can find that value. That is our expected value. Now, we expect standard deviation to be a little bit more difficult. Again, from the language here, let capital X represent the number of volunteers who have this genetic condition. So that's, again, our binomial distribution. Find the standard deviation for the probability distribution. That sounds a lot more complicated than it is. But you can imagine that this 95% of 170, that 95% of 170, what's 95% of 170? I can find that value. 95.95 of 170 is 161.5. So 161.5, that's the expected value. That's going to be the average. That's the peak of our distribution. So that's the highest probability that we have. But, there is a standard deviation. There's a spread in this data. Is it possible to get, say 163 instead? Is it possible that out of this 170 people, 163 will have the genetic condition? Sure, it's possible. Is it possible that 150 people will have it? Sure, it's possible. Is it possible only 50 people will have it? It's possible, but it's really unlikely. That would be very unusual. There's an unusual question down here somewhere. Very unusual for it to be that low. So if we want to know, well, how distributed or how should these values be distributed, having an idea of the sense of spread would be good and reasonable. So to do that, we'd have to figure out what that standard deviation is. Now, you remember finding standard deviation by hand. Now, again, we're using sigma because it's a population, but still means standard deviation. And you might remember that big formula, you know, that sample standard deviation was the square root of the sum of the individual deviations squared divided by one less than the sample size. If it happened to be a population value, a mu, it was, you know, just divided by the sample size itself. Finding means for binomial distribution, or finding standard deviations for binomial distributions, is much more straightforward than that. We don't have a bunch of different values. All we have is a bunch of yeses and nos, a bunch of probabilities, a bunch of either 95% chance of yes or a 5% chance of no. So it really simplifies the calculations down to a very nice little formula. Okay, it still has a square root in it. But instead of being that kind of big, icky formula, it is simply the square root of n times the probability of success times the probability of failure. That value is our standard deviation. So in this case, we've got 170 folks. We're multiplying that by the probability of successfully having this genetic condition, 0.95, multiplied by the percent chance, the proportion that won't have that condition. So subtract it from 1.05. By the way, I'll often use Q to represent that 1 minus P. So often you'll see this from me and from others as NPQ instead. So P is the probability of success and Q is the probability of failure. Your book likes the 1 minus P, and a lot of people like the 1 minus P. A lot of people like using the letter Q to stand for that. It's an option. So this value that we would get from that would give us a standard deviation of how much spread there is here. So real quick, I'm going to find that value, not forgetting to take the square root. It is easy to forget to take that square root. So it's 2.84, I'm going to say. Well, how about just 2.8? I don't know how many decimals I told you to take here. Which means round up to the whole number, huh? Oh, okay, so I'm gonna go with the 2.8 and then round it up to the whole number when we're done. So this 2.8 gives us what that spread should be. So that means our spread, our average was our mean average was 161.5 with a standard deviation of 2.8. So typically we'd be within 2.8 people of that 161.5. It would be unusual to be outside of 2 of those standard deviations. So 161.5 plus 2 times that standard deviation, 2.8. That's going to give us our high bound, and 161.5 minus 2 times the 2.8 is going to give us our low bound. So let's find that. 161.5 plus 2, because again, we want 2 standard deviations from our mean. 2 times 2.8. That's 167.1. 167.1. Now, find the range, or find the range rule of thumb, use the range rule of thumb to find the minimum usual value and the maximum usual value. So we would normally find a maximum of 167.1, but 167.1 is 167 people. Even if this was 167, say 0.8, then you'd have to ask, is 167 people unusual? Well, no, 167 people is still in the usual range. Well, what about 168 people? 168 people is outside of that usual range. So we don't want to round that up to get where our range is. 168 is bigger than 167.8, so it would still be unusual. So be careful. That's why it's telling you here where to round up and where to round down. It's not always going to tell you that, by the way. So with 167.1, we'd normally round down, but we have to round down here because we're talking about a maximum number of people. For the lower bound, the 161.5, the 161.5 minus 2 times 2.8. Again, this is the 2 standard deviations below the mean, is 155.9. 155.9. So again, is 155 people unusual? 155 is lower than that. So that would be considered unusual. So the smallest amount we would still consider usual would be the 156 people. So our range is going to be from the 156. And again, we'd round that up even without that 9. So the 156, as long as it wasn't 0.0, 156 to 167 is where our usual range would fall. So the same ideas for usual. It's 2 standard deviations above and below the mean. Same idea of mean and standard deviation. Mean giving us a center, standard deviation giving us a spread. But because we're dealing with these binomial distributions, because we're dealing with the probability, we've got different ways of finding standard deviation and mean. And the nice thing is that they are a lot nicer. You know, finding mean by just NP, that's nice. That's our expected value. That's nice. Finding standard deviation just by this NPQ's square root, also very nice. So hopefully that helps. Let me know, and I'll talk to you guys soon.